All right, the evidence for wave or particle nature of light continued here. So we're going to look at Einstein and his prediction of the effect of gravity on light, which is a very particle seeming thing. Light and the conservation of momentum, also particle thing. Refraction, though, very wave-like. So, yeah. So in 1905, Einstein predicted that light is affected by gravity. General theory of relativity. And so, of course, very particle nature-ish, right? As seen yesterday, though, the universal wave equation works and so on. So that's very wave-like. So kind of the debate continuing, but Einstein's prediction, his work to do with general relativity and describing gravity as curvature of space-time and so on, led him to realize or predict that light would be affected by gravity. And so there was a solar eclipse happening soon after that. So he told the astronomers of the world, got them to look and see if a star would be in a different spot than normal. So the star's actually here. Light comes along, gets bent by gravity, and ends up looking like it came from this direction, right? This direction here. So from your grade 10 science light unit, hopefully you saw the idea of like, okay, well, the light looks like it came from a spot. Well, then you see an image of the thing at that spot, right? And so, light is affected by gravity. It asked he got the world to look and see if that star was in a different spot, and sure enough, it was. So picture like the Big Dipper, but one of the stars is out of alignment. So very obvious and very measurable, and a huge confirmation of the general theory of relativity. So yeah, light is affected by gravity, super particle kind of property. Although there's a little bit of a twist. Obviously the mass of a particle of light is 0. So how can gravity, be affecting it? So just one sec. All right, here we go.
We're all familiar with gravity as the reason objects fall, but there's much, much more to gravity than that. Gravity is a long-range attractive force between all objects with mass. It's what keeps us from falling off the Earth, it's what keeps the Earth in orbit around the Sun, and it's what caused the Sun itself to form 4.5 billion years ago. It's amazing to think that every massive object attracts every other in the universe. That means that your dog, the Earth, and a black hole in the Andromeda Galaxy 2.5 million light years away are all gravitationally attracted to you, and you to them. In the 17th century, Isaac Newton discovered that the strength of the gravitational force decreases by the square of the distance between two objects. So if you're twice as far away, gravity is only 1/4 as strong. He also discovered that the strength of gravity is proportional to the mass of the objects in question. The more massive an object, the stronger the gravitational force. That's why we can all feel the Earth pulling on us, but don't really notice the pull of the moon. It's smaller and farther away. The moon's gravity is strong enough to cause the tides, though. And when I said earlier that gravity is an attraction between objects with mass, I lied. I meant objects with energy. Because in addition to massive objects, gravity also attracts light and other massless but energetic particles, so that a photon of light can be bent slightly passing the sun or trapped completely by a black hole. Now do you understand the gravity of the situation?
So yeah, that's the kind of the extra bit of information there that they don't even mass, but they do have energy, and it turns out that gravity attracts mass and energy, which is strange. But I mean, you just have to become more familiar with the general theory of relativity, and then it's not as strange or not as unfamiliar, right? But yeah, gravity attracts energy, and there's a connection between energy and mass, and it's to do with the classic E equals mc squared, right? So your proportionality constant is that speed of light, the proportionality constant between energy and mass. And yeah, all right. So if light's made of particles, can it reflect? Well, yeah, and it can reflect. Sorry, the law of conservation of momentum could be tested. So this is a radiometer, and so has white sides and dark sides, black sides of these little veins or these little vertical surfaces. So if light shines on the white, it reflects, and if light shines on the black, it absorbs, right? So here's an announcement or analysis, of the momentum of this kind of situation. All right, so on the black side, we've got the mass and velocity of the light coming in, the mass and the velocity of the vein. It's at rest to start. On the white side, again, velocity of the light would come in, And again, the vane is at rest at the start. So on the black side, the light becomes part of, right? It absorbs, becomes part of it. So you're going to have the velocity is the same. It's going to be the same as the velocity of, the second velocity of the vane itself. And so you have the m1 plus m2 combined. On this side, it's going to reflect, right? So you're going to have this is a negative value. So we're going to have a negative m1 here, negative m1 v1 prime or whatever. And so we have take away a negative here, right? And so this becomes m1 plus m1 v1 plus m1 v1 prime. So if you look at the values of these things, we've got v2 prime, so the final velocity of the metal vane is going to be m1 v1 divided by m1 plus m2. This one is going to be m1 v1 plus m1 v1 prime, so it's quite, it's bigger in general, plus it's divided by something smaller, right? So just through easy analysis there, you can see like this is going to be the one that wins. This is going to be the bigger effect, right? So yeah, because of the larger number divided by the smaller number idea there. So yeah, so it should be rotating so the white side trails, because this side, there's going to be, if you add these two velocities together, you're going to have the one where it's going to be going that way, if that makes sense. So it's the radiometer that I have in the classroom here. So there it is. Turn the light on, and it turns, right? So you're like, oh my gosh, it works. Conservation of momentum. But then you look at it a little more carefully, and you see that you think maybe it confirms conservation of momentum. You look at it more closely, though, but it's spinning the wrong way. So it's not to do with conservation of momentum. Instead, it's actually to do with thermal energy, right? So the black surface, now inside of that radiometer, there's a decent vacuum, but there are still air molecules in there. And so, the black surface heats up more because it's absorbing the radiant energy, the infrared. And so it gets hot, and then the particles next to it bounce around more and hit it more and kick it and make it go, right? So it's actually air molecules. It's not conservation of momentum of light at all in that thing, right? So apparently the story goes where they made this thing and realized hey, this could be a confirmation of conservation of momentum, built the thing, saw it and celebrated and was super happy, and then basically later on noticed it was going the wrong way, and it's like, oops, wait, the Nobel Prize for confirming conservation of momentum apparently not going to be granted. So I was told this story by the teacher I taught with in Brockville when I was a student teacher, and I've always just sort of relayed the story to students. This year I threw it into ChatGPT just to see what it would say. Is it true that, and so on, and it said basically, yeah, it's kind of true. It's Crookes radiometer apparently in the 1870s, and again, they thought it could be radiation pressure, like conservation of momentum, essentially pushing on the vanes and so on. But of course, the problem is it goes the wrong way. As I said, what's actually happening is the thermal energy pulled up all the stuff that I've been saying for years, right? So is it true that they're very excited and disappointed? And so basically, yeah, it's sort of what happened. Yeah, scientists quickly questioned it though, right? Did see the light pressure effect, basically proposed that it was conservation momentum, but it got vetoed or checked pretty quickly, I guess, right? And so yeah, over time, experiments showed that it was really due to a small amount of gas in there and so on. Fun twist though, the radiation pressure is a real thing, and so it was confirmed, by this person later on. But obviously, it's way too weak to drive the Crookes radiometer in that way, especially because it isn't a true vacuum. So to do with this though, it's a real thing here. Like laser propelled spacecrafts is a possible thing. I don't know for sure about the credibility of this video. Watch it though; it's kind of fun. I'm not going to play it here because possible copyright infringement and whatnot. But yeah, it talks about the mechanics of blasting a laser off of this sail that would carry a spacecraft to Mars, possibly in like 72 hours, because it can reach like 30% of the speed of light in theory. So possible future of space travel, who knows, right? But yeah, watch it with some skepticism, I would say. I didn't fully vet and check this out, but it's interesting concept, at least I would say, at this point. So the evidence continued here, right? So of particle or wave nature of things, right? So Newton basically thought, okay, well, refraction could happen if it's refraction is a change in the direction of a wave due to speed change, right? So light is seen to do this, and waves are seen to do this. So Newton said, well, particles could do it too. If you're changing direction, changing speed, you have a little ramp here. As the ball goes along, it gets to the ramp section, it's going to fall down a fair bit, and it's going to change direction as a result. And so basically predicted that the refraction would bend towards the normal. And so the angle of incidence, this is called the angle of incidence here, and then the angle of reflection to the green there, that it would decrease. Wave analysis, of course, is the opposite, right? So I describe this as like wheels of a wagon coming in. And so coming in parallel here. Let me grab a little bar to show the idea here. So if this thing's coming in, right? If this one's speeding up, it's going to travel further than this one. And so basically in the time that this one goes to here, this one will have gone all the way out to there. So that's how we're getting that change of direction, right? That's the idea of refraction of waves. And certainly the Huygens principle, shows that it works as well, and so on, right? So this is the opposite prediction of the way Newton would think it would go, and of course it's the way waves and light actually go, right? So it's pretty big evidence of wave nature, right? Observations show that light refracts away from the normal when it's going into a faster material, so pretty solid evidence of wave theory. This wasn't known at Newton's time, so Newton didn't just ignore it or whatever. Basically, it just wasn't known at the time because speeds of light and the details weren't known yet. So yeah, there are times later on in when I'm showing this later that there was good evidence against particle nature, and Newton just refused to accept it. Right? This isn't one of those cases, but it's actually kind of a common thing in science. There's really well-known, well-accomplished scientists will refuse to accept things, and then eventually, the truth wins, of course, in science, right? Because everybody questions everything in science. That's what we're trained to do, right? We don't just accept what someone else said. We look into it further and follow the evidence, right? So some background detail for grade 11 people that didn't see the waves and sound stuff. We have this idea of refraction, and if you look at the numbers here, angle of incidence and angle of reflection, and what the connection is, you might think, oh, well, maybe it's always like divide by 2, or maybe it's always multiply by 2, or maybe it's always square root or power or whatever. Some kind of, you're looking for a relationship there, right? Whenever you're looking for a relationship, you want to end up finding a straight line, because then you could say, oh, well, it's proportional now. We can get an equation, right? So if possible, right? And so it turns out sine of the angle of incidence divided by sine of the angle of refraction makes a nice straight line. And so we end up with knowing those are proportional. And so you divide both sides. You say, okay, that's equal to a proportionality constant. And so that is what we call the index of refraction. Basically, it's a measure of how much bending there's going to be. That's what that turns out to be. Okay, so yeah, the index of refraction for a vacuum is obviously defined as being 1 because it's the fastest speed stuff, right? And then into air is a slightly bigger number. Vacuum to water, light slows down a bit more in water, so it's a 1.3. Diamond, it slows down a lot, so 2.42. Those are just your indexes of refraction that are related to how much of a change in direction there is, which is related to how much of a change in speed there is. Right? So that'll all come together on the next page here. So for now, we've got, this index of refraction, sine of angle I or sine of angle R, just like from grade 10 science. Possibly you saw it somewhat at least, right? If not seeing it for the first time ever, well, so be it. But I mean, it's an equation, it's a relationship that's true. It turns out that this index of refraction is actually a ratio itself. It's a ratio of index refraction of the material divided by the index refraction in a vacuum, but that's just 1. So in grade 10, it can just be simplified to that, right? But actually, it's this. Index refraction of the refractive material, the one the light's going into, divided by the incident material is equal to the sine of the angle of incidence over the sine of the angle of refraction. So they're kind of opposite to each other, which is weird and annoying for that equation, but if you multiply both sides by the angle of incident or index of refraction, sorry, and the sine of the angle of refraction, it becomes a little bit easier to memorize. Ni sine angle I equals Nr sine angle R, right? Index of refraction of the incident material times the sine of the angle of incidence in that material equals the index of refraction of the refracted material, the one that the light's going into, times the sine of the angle of refraction. Okay, so that's the real version of Snell's law. So that's kind of new for everybody. And then it was also found to be to do with the ratio of the wavelengths as well. And then we know the universal wave equation. Wavelength is v over f. And so because the frequency doesn't change, right, then it's a ratio of the speeds. So this is the equation from grade 10, right? The index of refraction is c over v. It would have been written as speed of light in the vacuum divided by speed of light in the material. Okay. If you put all of that together, you've got multiple versions of Snell's law, right? You've got the ratio of the index of refraction. You've got the ratio of the angles of sines of the angles of refraction. You've got ratios of the speeds, and you've got ratios of the wavelengths. Okay, so that's the full deal. And then in a question, you just pick the parts that you're going to use, right? So in this case, we've got indexes of refraction and we've got speeds. So that means we're going to use the index of refraction and the speeds part, right? So let's just circle here. We've got indexes of refraction, which is this stuff, and we've got speeds, which is this stuff, right? So obviously we're going to use those parts. You're going to see that there. Okay, so that means that stuff. And yeah, put numbers in and solve, or solve then put numbers in. Okay, this gives you the velocity of the red light in the glass, apparently. And then it says, what's the wavelength? Well, my preference would be, we're working with wavelength now. Yeah, it gave you the wavelength, right? So if we're working with wavelength, why wouldn't we just use wavelength and the index of refraction stuff, right? So that would be, index of refraction stuff. So this would just be using the original numbers and, generally considered kind of better, right? You're not using a number that you might have made a mistake on. For some reason, the original resource where this came from, they used that number. It's not the end of the world. It still works, but you'd get the same answer provided there weren't any errors, okay? So that allows you to calculate the wavelength in that glass. So you'll see the wavelength reduced, right? It went from 6.5 times 10 to the 2 down to 4.28 times 10 to the 2 because it's going into a slower material, right? So you have a wave in the time the vibration goes up and down. The wave travels this far, kind of thing, right? So that wave, if it goes into a slow material, isn't gonna get as far, right? So as this thing goes into a slow material, it's only gonna get half as far if it's slower, right? So it's gonna pile up. It's gonna decrease its wavelength. Just to try and give some context background info from grade 11 to remind or show it to you for the first time ever. So some neat examples of this. There's of light doing this, right? So light has other properties as well to do with polarization, which we'll see later on. Possible wave properties of light later on. But this is a weird material. It has a double refraction. So that video there we can probably see quick. So that's a piece of that material. It has a little double refraction. And then I think I have another video later on that'll show where if you use a polarizing filter, you can see one of the double images, and then when you turn it to a different angle, you see the other one. But we'll talk later about that when we talk about once we get to polarization. Other things that light does, and so it's observed as a light thing, right? Total internal reflection. If you haven't heard of it, you probably heard of fiber optics and prisms and so on. But yeah, if light refracts towards the normal because it's going into a faster material with that same analysis, again, I'll do it here, right? Have the thing going along here. And now it's going to go in, and this one's going faster now, right? I think it's the same as what I did before, actually, right? And so it's going to go faster and change angle like that. If it runs out of room to refract, a weird thing happens. It reflects. Not only reflects, but reflects really, really well. Okay? They call it a total internal reflection. It's way better than a reflection off of a mirror. So if you analyze Snell's law, you've got this angle of refraction becomes 90 degrees, and then what that allows you to do, if you know the two indexes of refraction for the materials, allows you to solve for the angle that happens at, and that's called the critical angle, right? So basically light can go straight through, but as you go on an angle and an angle and an angle further and further, eventually you get to a point where it reflects instead, right? So once this ray gets to here, instead it reflects, which is strange, because you think of this as like water and then this is like a vacuum or air. Really, the light is reflecting off of nothing, and it just happens, right? It's one of those things in life that we can't necessarily really explain why it happens. It's just observed to happen. In grade 11, I talked about it could be other options. It could have just absorbed, the energy just absorbs and heats up the material because there's nowhere for it to reflect. But that's just not what happens. It reflects, right? This is a weird, another mineral. This one was the calcite. This one's the lucite. This one's called the TV rock, and it has all sorts of like, they think of it as having these structures or fibers of the clear material. They're like little fiber optic cables. So light reflects, and ends up coming out in the same spot. So underneath there's a G, and then that G image, appears on the surface of it. So I'll show that one too, because the picture doesn't do it as much justice as looking at it. But yeah, you hold it on there, and it projects almost that image up to the surface, right? So that's another fun little physics substance, if you will, when you're talking about things like total eternal reflection. So now the particle versus wave thing, does sound do this? Do water waves do this? The answer is yeah. Like sound waves can be shown to totally internally reflect. It's not super obvious, but it really does. In grade 11, I talk about sound coming up to a warm layer of fog. And I'm in a boat over here. My parents are over here. And my friend John and I are talking, and my dad could hear us from far away because like the sound was like totally internally reflecting again as it tried to go into that warmer layer of air, that faster layer of air. So that was one time in my life where it was kind of obvious it was doing that. Water waves as well, mechanical waves. Apparently, yeah. Like they in a laboratory, researchers have shown this effect clearly that water waves in shallow water can hit a boundary in which go into deeper water, and if you have sufficiently large angles, it runs out of room to refract, and it reflects like very, very well back. Apparently, so it is total internal reflection. You don't see it in nature just because everything's so messy in nature, right? There's all sorts of other stuff going on. There's gradual changes of depths and dissipation of waves and all sorts of other friction and turbulence and other waves from wind and so on. But apparently that's a thing. So this is very much a wave property, and light is observed to do it. So I wonder what Newton would have to say about that. Other fun facts: polar bears. You're familiar with them, right? They're clearly white and so on, but apparently, or not apparently, it turns out if you study it, their fur is actually clear, and their skin underneath is black. You can see the black nose and whatever, but their skin is all black. And so, like, obviously, why would that be? Well, the white is the camouflage, of course, and the thermal energy from the black skin. Right, when it's sunny, they'd absorb a bunch of warmth and help them stay warm up in the Arctic, right? And so, it turns out the hair strands are like little fiber optic cables, and it channels light down to the skin and helps warm them up. And so, you might ask, like, well, why do they look white then? Well, that's just because the way the fur is, it also scatters, some of the light around and bounces it in sort of all directions, some towards the skin to warm them up, some away to look white, right? So since all visible wavelengths are scattered based on the molecular structure of the hair, the fur, all types of light are scattered, and of course, all colors of the rainbow combine to be white, right? So it's the same way like snowflakes look white. Ice is transparent, but if it's scattering a whole bunch of light, then it looks white. Weird, fun facts about things that not everybody would know. So it's a fun little party discussion. Be like, did you know? If you're that kind of person, if you're around people that like that kind of people, so there's a fiber optic. So this is total internal reflection. You got light coming along, goes into a faster material, wants to refract, but runs out of room, so it reflects, comes out the other side. Okay. Um, anyways, that's some stuff to do with wave and particle properties of light continued, and we're not done yet. It's going to be more of that to come. So keep your I don't know, eyes peeled for that, whatever you want to say. Anyways, I gotta go. Talk to you later. Bye.